So AMA, we've got 12.3, we've got day 2 of 12.3. Certainly we're going to look at some applications, but there's more than that. We did talk about geometric sequences that, had a common ratio. You can more or less multiply a constant to go from one term to the next. Series, this is where we're adding all those terms up. So, taking a look what we've got in this box here, what if we had an infinite sum? What if I didn't say, hey, add up the first 30 terms? What if I said, no, add up forever? So, that could get very interesting. Take a look here. This is known as an infinite geometric series. You can see that the top boundary of sigma here is infinity. That's how we could designate that. That's how we could represent that. Well, we're saying if this finite sum S sub n, if we only add it up to n, approaches a finite number L as n goes to infinity, we say that the infinite series converges. So in other words, we'd say, look, it sure looks like we are approaching a fixed real number. We keep adding things up. As we keep adding up, as n goes to infinity, add up the first 1,000 term, add up the first 1,000,000 terms. You're saying, wow, we just keep getting closer and closer approaching this number. You could say that that's what convergence really means. We call this number L the sum of the infinite series, the geometric series. If the series does not converge, if you're not approaching a fixed number, then we call that a divergent series. So the big question is, if we're adding up forever, we're adding up an infinite number of terms, how do we know when we converge and then when we wouldn't? And guys, it's right here. If the absolute value of your common ratio, if the absolute value of R is less than 1, the infinite geometric series converges. And wow, you want to memorize this thing right here. It converges to A sub 1 all over 1 minus R. Let's see this in action. We're looking at number 1. You've got a geometric series. You have a start. What's your first term here? Your first term has to be a 2. You can see that. K equals 1. This thing goes to 2/3 to the 0. It's a 2. And then guess what we're multiplying by each time? 2/3. Now, is the absolute value of R, the absolute value of 2/3, less than 1? Yes, it is. This converges. I can say most definitely that as we keep adding up forever and ever and ever, we're going to get closer and closer and closer to this. A sub 1 all over 1 minus R. Your A sub 1 is 2. Your R right here is 2/3. And 1 minus 2/3 is 1/3. What is 2 divided by 1/3? It's 2 times 3 over 1, which is 6. So what we're seeing is keep adding this up forever and ever and ever. You'll get closer and closer and closer to 6. Okay? So that's what convergence really means. Let's see an application. We've got a pendulum. And a pendulum, initially, the word initially means at a start. Initially, a pendulum swings through an arc of 18 inches. So you could even say that's your first term. But then it says on each successive swing, the length of the arc is 0.98 of that previous swing. So now look, of course I could work this out and actually find out what 0.98 times 18 is. But I don't even need to do that because it's saying each successive swing, you're just going to go 0.98 the previous length. This means that we have a geometric series here, or a geometric sequence series if we add them all up. Now, guess what our r would have to be? What are we always multiplying by? 0.98, right? So this is good review. This is going back to what we did last time after a long weekend. First of all, they're saying, okay, so what is the length of the arc just on the 10th swing? Just on the 10th swing itself. So you could say, well, last Friday we came up with this. We saw, look, here was your formula. A sub n, if you wanted to go to the nth term in this pattern, it's the first term times the common ratio raised to the n minus 1. So I could say on the 10th term, I've got my first term of 18, then I'll have 0.98, but because n is equal to 10, guess what n minus 1 is, obviously? It's 9. So this is where, guys, a calculator is definitely going to be used quite a bit here for these problems. We could say 18 times 0.98. We're going to raise that up to the 9th. And we can say, well, we're not getting a whole number. It looks like 15.007. So we could say 15.007 inches. Of course, when we've got a number of inches for an arc length, that doesn't have to be a whole number, right? Yes?
So for A, let's see, 0.98 to 18.
Yes.
Why couldn't it be like 18 minus 0.98?
Well, the word of always means multiply here. So 0.98 of means multiply. And another way to think of that is to say it's like 98% of a previous swing. That's something else that some word problems are going to say, like each successive swing is 98% of the previous swing. It's like saying multiply 0.98 to that. Okay? So now they're going to say on which swing is the length of the arc first less than 12 inches? Well, you know, here's something interesting. We could say here's your basic formula right here. And they actually want us to be less than 12. So we could just put in a 12 there, knowing that, honestly, we want our swing to really be even smaller than that. Yeah, and we're going to work with n, you know, to know. And you can see what's happening over time. Are our swings getting shorter or longer in each successive swing? Shorter, and that's physically what you'd be seeing is a, you know, clock pendulum or, you know, a chain swinger or whatever. You know, even at the playground, the swings, you know, eventually it's going to come to a stop. Well, you know, here's what's happening. We want to know when we're going to hit 12, but look at this. Wow, we're going to have to solve this equation. 12 equals 18 times 0.98 to the n minus 1. Okay, so I heard someone say divide by 18. Does that sound good? Right, so 18, by the way, 12 divided by 18 is actually a whole fraction, clean fraction rationally. We can go 2/3, divide out of 6 from both. So that can be good, but wow. Now what, should I divide by 0.98? No, you see, it's not 0.98 times n minus 1. That n minus 1 is way up high. Log, and ln on both sides. Very good. So I'm going to take the ln of 2/3. And over here we've got the ln of 0.98 to this n minus 1. And the whole reason for doing that, I'm going to slide over here, is because the log property said that we could have n minus 1 and bring it down. Now, guys, I hope it's clear as day to you too. I know this looks ugly, but we could, without a doubt, just divide by the ln of 0.98 right now so that we could have our n minus 1. So, tell you what, let's do that. Let's get our calculator out. Like I said, our calculators, we're going to need them today. We've got ln of 2/3, right? And you could do pretty print too. I mean, you could have made the fractions vertically stacked on top of each other. But what can scare kids is they'll say, that's not a whole number. Well, no, it isn't. It's 20.069 something. Yeah, and then you got to add one, right? Because it's n minus 1 right here. So we'd get n equals 21.069. And guys, understand what you're saying. On the 21.069 swing, that's when you're going to be at 12 inches. Now, is there a 21.069 swing? No. There's the 21st swing, and there's the 22nd swing, and so forth. Would the 21st swing be the answer? No. No, we're going to have to bump it up. It's on the 22nd swing, that we're going to have a pendulum arc that's smaller than 12. It's at 12 in between the 21st and the 22nd swing. 21st, you could even confirm if you wanted to. You could find the 21st term. It's going to be a little bit bigger than 12. When you go to the 22nd swing, you'd find that you're smaller than 12. Okay, we doing okay? All right. Well, take a look at number or letter C. They're saying after 15 swings, what's the total distance? In other words, they're saying add up all those swings. And that's a series, isn't it? Now, guys, from last time, I hope you remember seeing that this formula is what we came up with on Friday. We had that lesson where we said, hey, if you wanted to actually not find the nth term, if you said, I want to add up to the nth term, this was that formula that would do it. And you could say, well, at 15 swings, we're going to let n equal 15. So S sub 15 is going to be our first term. We already said that's 18. So we've got 18. And then we've got 1 minus, 0.98 all the way up to the 15th power. And then down below, we've got 1 minus 0.98. Now, could we simplify the bottom and, break it down step by step? You bet we could. But look, chances are very high it's going to be a decimal anyway. So tell you what, how about we just type things out. Here's 18 parentheses 1 minus our r of 0.98. Bump it up to the 15th power. And then down below, we can even say in parentheses 1 minus 0.98. By the way, in pretty print, you don't even need parentheses there. But evidently 235.288. 235 point, and I think it was, 288, and we said units were inches. So, wow, that's how many inches that pendulum has traveled after 15 swings, right? Now, here comes the irony of it. Is this an infinite series? No, I mean, very quickly, kids are going to say, now, everybody knows eventually that pendulum's going to stop. You bet it is. Of course it is. And we know that. But look, we don't know what swing it's going to be as it comes to its total stop. So here's what mathematicians are going to do, because eventually the swings get so super short at the end. We're going to say, look, our R here is 0.98. And the absolute value of R is less than 1. We could say, if we had an infinite sum, it would come to this. Now, we know it's not an infinite sum, of course. But what you can see numerically is if you look at these numbers, and if you begin to look at these sums, like the sum going up to the 15th term and the 16th term and the 17th term, you're going to see there's hardly any difference. Maybe we can even take a look at that. But that's going to be 18 all over 1 minus 0.98. We're running out of time, so let's do that real fast. We'll say 18 all over. And then we've got 1 minus 0.98. And the infinite sum would be 9.